This week we'll continue analyzing the real numbers in its connection with the axiom of completeness, or the least upper bound property. The fact that the real numbers, any bounded set of real numbers, any bounded set from above, has a least upper bound. That's referred to here in the book as the axiom of completeness, but we don't need to assume anything. We know the real numbers, the way we constructed them, have that property. The real numbers have the real numbers. Set of real numbers has this very nice completeness property, which allows us to, among other things, find a solution to the equation x squared is equal to 2, which is not possible in Q, the set of rational numbers. So now we begin this very short week. Because you have an exam, by analyzing what happens to the supremum when we perform certain operations on the set. This is example 1.3.7. So let A be a subset of the real numbers, be a non-empty set, and bounded from above. And we let C in R be a given number, just any given number. And so we define the translation of the set. We define the set C plus A by the set of all translates by C of elements in A. So C plus A, where A is in A. If you remember what we did when defining the operations for real numbers, so for Dedekind cuts, we define the notion of addition of Dedekind cuts, and these are subsets of rational numbers. So this is actually reminiscent of that. If you so the set C plus A in that definition would correspond to just adding the set C, the singleton C, the set that contains only the element C plus A. So that's what this corresponds to. So we're just adding every element in every element in A. So we're adding C to any element in A, and that's the set that we have now. And so if you think of intervals, I told you that you should start thinking about more general sets, but just to get an idea, this is just so it's not bad to use certain known sets as reference, but then you need to transform that into a proof. That's why I want you to forget about the intervals, but at the same time, that's what gives you intuition. But the intuition is not enough. So at that point, forget about the intuition, and once you know what's going on, try to write a rigorous proof using just the properties. So here we have the set A, and we add C to it. So that means that we're gonna translate everything here by C. So this quantity here is just C, and what we do is we shift everything here to C. So this point over here that we don't know yet what it is, may belong to the set A or may not, but this has to be the supremum. You probably already have you already understand that this should correspond to the supremum of the set. And what happens to the supremum of the set? So this is the set C plus A. We translated the set A by C, by a number C, by adding a number C to each element in A. So this number over here, which would be the supremum of the new set, should be equal to what? So we translated everything here by C, so this should correspond to translating the supremum by C as well. So this is in fact the 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 content of this statement here, so that the the purpose of the example is to show that this is actually the case. So what we can see here in this drawing, this should just give us an idea what we should expect, and then now will come the proof that that's indeed the case. So this is the conclusion here. Then the supremum of C plus A is actually just C plus the supremum of A. Okay, and how do we go about showing this? This is proof. So we want to prove this statement. So we need to show two things. If we add C plus the supremum of A, that will be an upper bound. And if we have any other upper bound to the set C plus A, then that will be greater than or equal to this bound here, and thus making it the supremum. We already saw last week the supremum if it exists for a set, then it is unique. So there are no two supremums. There's only one supremum. So once you show that something, that a certain number satisfies these two properties, namely, it is an upper bound for a set, and if you have any other upper bound for the same set, then it is greater than or equal to this upper bound, then that must correspond to the unique supremum. Okay, so let's set some notations. S is going to be, just to avoid carrying this around, so S is going to be the supremum of the set A. So what do we want to show? We want to show two properties. We want to show that for any element of, let's just write it using mathematical notation. So for all A, maybe just reserve the lowercase a for the set A. So for any x in the set C plus A, if you wish, I mean, you can use just y or r for real number. Any r in the set C plus A, we want to show that r is bounded from above by the C plus S. This would show, this shows, or this would show, if this were the case, which it will be, this would show that C plus S is an upper bound for the set C plus A. Let's pay attention here. We're picking any element R in the set C plus A, and we are arriving at the conclusion that no matter what R is less than or equal to C plus S. So C plus S will certainly be an upper bound for the sets C plus A. Okay, so this is what we want to show. So yeah, okay, then again, I'm repeating myself. So this shows that if we pick any element in the set C plus A, that will be bounded by C plus S, and this shows that this is an upper bound. We're first showing that C plus S is indeed an upper bound. Then we'll show that the C plus S actually satisfies that it is the least upper bound. Okay, so this is what we want to show. So all we're saying here is what we want to show. So let's try to show it. To see that this is the case, let us note that if R, there is an R that belongs to the set C plus A. If it belongs to C plus A, it means by definition that it must be a number that can be written in this way: C plus some element in A. So it belongs to the set C plus A, then there is an element A in A such that there is an element in A such that R is equal to C. I'm sorry about that. So it's equal to C plus the lowercase a. Why? Well, we know that any element in C plus A is of the form C plus some lowercase a, where a belongs to A. So what do we want to show? That C plus A is smaller than C plus S. This is what we set ourselves to prove from the beginning. We've written R as C plus some number A that belongs to the set A. We know we have to start from things we know that we have. So on the other hand, we know that A is less than or equal to S. Why? Because S is an upper bound. Remember that it's the least upper bound is the supremum. It's an upper bound. It's an upper bound for the set A. And since A belongs to A, then S must bound that number. We may then add C on both sides, so adding C on both sides gives us that A plus C is less than or equal to, or C plus A, just to be consistent. I mean, it doesn't really matter. You know that addition is commutative. Is less than or equal to C plus S. But what is C plus A? Is equal to R, right? So we've shown that R is then less than or equal to C plus S. So what have we shown? We've shown that C plus S is an upper bound. So we have shown that C plus S is an upper bound okay, so now we must show that C plus S is actually the least upper bound. So let's now let let's just be an upper bound for the set C plus A. Any upper bound. So this means that for all R in C plus A, R is less than or equal to B. Okay? This is what it means for B to be an upper bound. It must bound any element in C plus A. I mean, this is an upper bound for C plus A. It means that it bounds all the elements in that set. In this case, the set is C plus A. Now, for all R in the set C plus A, R is equal to C plus A for some A in A. Right? Of course, the A depends on R. But given any R in the set C plus A, there is a corresponding lowercase a such that R is equal to C plus A. Remember that all the elements in C plus A can be written, are the elements of the form C plus A, where A is in capital A. Okay, so these are all the elements in C plus A. So all the elements are in C plus A are of the form C plus A. So now, what are we saying? So then this implies then that, or we, okay, no, let me rephrase it. So then from the fact that B is an upper bound for C plus A, we deduce, so, or C plus A, it must be true that C plus A is less than or equal to B. Why? Because B is greater than any R in C plus A. But any R in C plus A is of the form C plus lowercase a, as is indicated here. So that means that it must be true that this, and this is true for all. So what is arbitrary here? The lowercase a for all. So I mean arbitrary as long as it belongs to the set A for all A in A. And so this implies now this implies that A is less than or equal to B minus C, right? And for any for all A in A. For all A in A. But this means then that, so this means that thus B minus C is an upper bound for the set. It's an upper bound. It's an upper bound for the set A. You see, B minus C bounds from above any element in A. So it must be an upper bound. But if it's an upper bound, it must be bigger than what? So therefore, we can put this in here. See, since it is an upper bound, what can we conclude? Therefore, B minus C must be greater than or equal to S. As I said, B minus C is an upper bound. And any upper bound for A must be greater than or equal to the supremum. Remember? The supremum is characterized by two properties. One that is an upper bound and one is the least upper bound. Meaning if you have any other upper bound, in this case B minus C, then this must bound S from above, so the supremum from above. And this implies, of course, that S plus C, or C plus S, if you add C on both sides, is going to be less than or equal to B. And if we go back to what we are trying to show, is that if we have any upper bound for the set C plus A, then B must bound C plus S from above. And this is exactly what we've done here, what we would have accomplished here. So here, the conclusion is that we have a least upper bound then. So this allows to conclude, okay, let me just rephrase it. So this shows that C plus S is the least upper bound for C plus A. We already shown that it's an upper bound. Remember, we showed already that C plus S bounds all the elements in C plus A. Now we've shown that among all the upper bounds, this is the least upper bound, because we picked an arbitrary upper bound B, and we've shown in here in the box that B is greater than or equal to this C plus S. So far, C plus S was just a candidate for the least upper bound, but we've managed to show that it's indeed the least upper bound. and this is how all of these proofs go. You always have to go back to the definition and think about what you want to show. So this is something it may be worthwhile stopping by. So we want to show that something. So this is what we want to show. Whenever we write down a proof, we make something very specific. We set some very specific goals, and we try to follow very clear steps so as not to get distracted. So let me see that we can actually do this. Okay, and what are the first steps? What is the first step? Here we said we wanted to show, so I need to move this thing. Okay, so the first step was that C plus S is an upper bound. Per bound, so that means that C plus S bounds any R in the set C plus A. The second step was to show that C plus S is the least upper bound. Okay, so it's the least upper bound, and that means upper bound, and that just means that if B is an upper bound for C plus A, then C plus S must be smaller than or equal to B. So these are two very clear goals. So we want to show something in the first step and something in the second step. And how do we achieve that? Because I mean, this would be really hard to prove, except that we already know that S is the supremum of the set A. So what? And so here is the thing. So here there's a corresponding statement that we know. So we know what we know. So that's what you have to use to prove these two separate statements or related statements. So we already know two things that we can use, and each one corresponds to one of the steps here. We know already that S is an upper bound for A, and so this means that A is less than or equal to S for every A in A. We know this already. And so how do we obtain the corresponding statement over here? We simply add C on both sides, and that's the key thing. We're starting from here. A is less than or equal to every S, and we have to transform that into this to this statement, to this statement over here, that R is less than or equal to C plus S. And how can we do that? We simply add C on both sides, because every R in C plus A is of the form C plus A. Okay, so that's the first thing that we know. So that's 1, say, and 2, which corresponds to the other thing, is that we already know that if B, or let's just call it something else. So if we have another upper bound for the set A, if K is an upper bound for the set A, then A is going to be greater than or equal to S is going to be greater and less than or equal to K. So how do we use this information to prove this? The second part, which is the second step in our proof that C plus S is the upper bound, because if C plus S, you want to show that C plus S is less than or equal to B, we try to show this. B minus C is greater than or equal to S. So you want to show then, how can we conclude that? If we make this a K. So if we manage to show that this is an upper bound for A, then we'll be able to show then that K must be greater than or equal to S. And in that way, B will be greater than or equal to C plus S. It will be, yeah. b will be greater than or equal to c plus s. And that's how we think about these problems. The next application we'll see will be the same thing for the product. I hope that once you've become accustomed to these kinds of proofs, after seeing this example in the next one, you'll immediately spot what you need to do, which basically just amounts to chasing definitions and to using what we know to show the corresponding statement 1 and the corresponding statement 2. Okay, so that's what we'll do next.